Yep. Welcome back to the afternoon session of the training module run. We start with a slightly different topic now with accounting. So using a supercomputer is free of charge for your researchers. So they apply to send an application to ask for time on the supercomputer. They are not charged for it, but the supercomputer use is limited. So you have a finite amount of resources of time you can run on a supercomputer in a year, and it has to be fairly divided across the researchers, meritorious researchers who actually are willing to use it to do their own research. As such, we need to quantify what is the consumable resource within a supercomputing environment, and we need to keep track of how much each user or each project is using, and establish the total amount of this supercomputing resource, and then distribute the resource or time on the supercomputer fairly across researchers. So in this module, we will review the accounting model for Cetonics. We will describe the accounting model, tell what it is, and what is a computer allocation. We'll go into the details of how this accounting model is implemented on Pawsey, and we'll show how you can monitor your compute allocation. So supercomputers are very expensive to buy and then to run, and they have to be replaced typically every 5 to 8 years, and they consume electricity whether they are being used or not. So the goal for Pawsey and for any supercomputing facility is to keep them as busy as possible throughout the years at every time to make useful computations to create quality science. There are three aspects we can control to make that happen. So the accounting model, so define and how to measure compute resources utilized by users. The compute allocation is a way of partitioning the total amount of available compute resources across projects every year. And then the job scheduler is the software that takes care of organizing and orchestrating the various computations on the supercomputer such that resources are utilized optimally and researchers get their fair use of the supercomputer. These three elements together are what are designed to maximize the utilization of supercomputer and at the same time make the science for every researcher possible. So an accounting model is a mathematical model that defines and measures the usage of resources of a compute infrastructure. The unit of measure we use is the service unit. So the definition of accounting model as service units they're quite tied together. So the service unit, once you define what you want to measure and define as consumable, then you have the service unit indicating a unit of such resource. Historically, it has been that a service unit was equal to 1 hour use of a CPU core on a supercomputer. So CPUs are always there, but the time, the CPU hour, or that means that the time that CPU can be used every year is limited. So you have, let's say, 360 days. You would like that CPU to be used 360 days. If one day goes to waste, then you cannot go back in time and use that time on the CPU. So that's why it's consumable. And hence, we used to measure the utilization of a supercomputer based on the number of CPUs you're using multiplied by the time you're using them. Nowadays, the supercomputing architecture is quite heterogeneous, and in practice, we see a lot of GPUs on modern supercomputers. In fact, most of the computational power comes from GPUs. So we need to introduce a different definition for a service unit, a different accounting model that defines a service unit. At Pawsey, we retain the definition that one CPU, for the CPU partition, one CPU hour is equal to one service unit. So every time you run your job for 1 hour on a CPU core, you consume one service unit. Instead, a GPU, 1 hour use of one of the two GCDs of one GPU. So to make it simpler, 1 hour use of one virtual GPU or GCD on Cetonix is equal to 64 service units. So the use of the entire GPU that is comprises two GCDs is 128 service units per hour. I will briefly explain how we came up with that number, but these are essentially the two fundamentals definition for service unit based on whether you're using a CPU or a GPU. So the cost for a job, so if you have a computational job, you submit it to the scheduler. Once it's done executing, you will be charged an amount of service units. And that amount is equal to the number of CPU cores requested multiplied by the work time, which is the time it actually took for the job to execute. And or if you're running on a GPU partition using GPUs, then the total cost would be the number of logical GPUs, GCDs, multiplied 64, multiplied by the work time. So that's how you will be charged. Your job will be charged. Based on this definition, you can also compute how many service units you have throughout the year to divide across researchers. So you multiplied, the total available CPU cores on Cetonix multiplied by the hours in a year, and then you get the service unit allowance for the CPU partition. Then you have the total available GCDs multiplied by 64 multiplied by hours in a year, and you get the total amount of service unit that you can on the GPU that you can distribute across projects. So a compute allocation is essentially it's part of this total that is then assigned every year at the project, at every scientific project. As each one of your internship projects will be assigned an allocation that is a certain amount of service units, and every time you run a job, a small part of the service units will be consumed until you reach 0. One thing in particular that we noticed when we defined these accounting models is that in the past, the consumable resources were only considered the CPUs and now GPUs, right? But there are other resources that also impact the use of a node on the supercomputer, in particular the CPU memory available. If, for instance, you are running a single core job on a node that has 128 cores, then you're using a very small fraction of the cores. But if your single core is using all the memory available on the node, then you're making basically impossible to use the other cores to other people. So what we do is we take that into account, and what we charge is actually the largest fraction across all the resources utilized by the job. This is an example. Well, I must say you can actually, on Cetonix, you can request a fraction of a node. So your job doesn't have to use the entire node or all the GPUs on a single node. So you can request one CPU core, or you can request one single GPU and a few cores. You have, there's quite you can ask a fraction of a node essentially, and you'll be charged for that. However, then we call that fractional usage of a node. However, this fraction does not depend on only on the number of cores, but also on the memory you're using. So in this example, we have an illustration of resources consumed by a job. We're using 1/2 of the CPU cores, but we are using 2/3 of the memory. What we will be charged for is the 2/3 of the node, because essentially we are using the largest fraction is 2/3, that is the RAM consumption. And the logic is that you're using the portion of the RAM assigned to a core that you're not actively using or requested, but you're consuming its dedicated or like associated amount of RAM of memory, and so the core is essentially out of memory and cannot be used practically by other jobs. So what we do is essentially mapping the memory usage to CPU usage. In this case, the way it is implemented in the system is that we are saying you're using 4 cores, even though you requested 3, but you're using the RAM also of the other core, of this 4th core. So we are actually in the counting model, we say you're actually using 4 cores instead of 3. The other example is the kind of the opposite. We are using 2/3 of the CPU cores, but we are using only 1/3 of the RAM. We are still charged for 2/3 of the node because in this case the largest fraction is the CPU cores, and then we are charged 2/3 even though we use less RAM. Any questions so far? On GPU nodes, we have a GPU nodes. On GPU nodes, things work similarly, but in a different also work similarly, but with the complexity that you have now also GPUs. You not only have CPUs, you have RAM, you have CPUs, RAMs, and GPUs. And given these are GPU nodes, what we want is that people use these GPU nodes for the GPU. So the main resource to be used on a GPU node is the GPU. And what we say is that you select the number of GPUs you're using, and you will be charged for that, and you will be given the equivalent fraction of the other resources. So let's say you are using all the GPUs, then you're given all the memory on the system, and you're given all the CPU cores on the system. You're using half of the number of the GPUs available, then you will be only given half of the memory and half of the CPU cores, and so on. There are 8 GCDs or virtual GPUs, so the allocation goes in multiple of 8s or 1/8. So you get 1 GPU, then you also are given 1/8 of the CPU cores and 1/8 of the memory, and so on. So when you write your own job scripts, you only ask for the number of GPUs, and the other resources are allocated and charged for automatically. So the minimum cost, so a single GPU costs 64 service units. So the minimum cost to run a GPU job is 64 service units per hour. The maximum is 412, which is 64 multiplied by 8. And in both for CPU and GPU jobs, if when you submit a job, you can specify, and you will see it later in the later module, you can specify a work time that is, this job, I want this job to run no more than 5 hours, let's say. So that helps the scheduler to place the job in on resources that won't be used for the next 5 hours, so that those can be given to you. But if your job finishes earlier, let's say in 3 hours, you will only be charged for 3-hour use, not the initial time you specified in the script. So here is a few examples of the, so far, any questions so far? Okay. Here is a few examples on how some jobs would be charged on Cetonix. So running one day on 8 CPU nodes is the equivalent of 24 hours one day, multiplied 8 nodes, and there are 128 cores per node. So the total amount is this 24,500 service units. So running for 6 hours on 4 cores within a node, requesting 115 gigabytes of RAM, that is half of the node, then you see that the fraction of cores is 0.03, but then half of the node in the terms of memory is 0.5, then you will be charged 0.5 in terms of fraction of resource, multiplied by 6 hours, and 0.5 by the total amount of cores, so 0.5 by 128, so this is the total. Running for 10 hours on 2 GCDs, or 2 virtual GPUs, in a GPU node, then you will be charged 10 hours multiplied by 64 by 2. So this is 1,280 service units. And so on. So one thing you will notice is that essentially you can think of a CPU core as a multiplier of 1 at its cost, 1 hour, so it's one service unit, but 1 hour on a single GCD is 64. So let's say a GCD costs 64 times more than using a CPU core. So it's more expensive to run. But the idea here is that a GPU, when used properly, can execute way much more flops or floating point operations per second. So what you get for that amount is much more than the actual, if used properly, than the actual cost. If you would have to run the same amount of flops on a CPU. In the way we define these weights, so 64 service units for 1 hour GCD, is by looking at the speed up usual applications usually get using. We've been looking at different things. We've been looking, first of all, at the energy consumption, so and the energy efficiency. So GPUs are in absolute terms more expensive to run than CPUs. They consume more power, but they also deliver much more floating point operation per second than a CPU. So if you measure the compute efficiency as number of flops divided the TDP, or thermal design power, or the maximum energy consumption for the device, then you see that the energy efficiency of GPU is much greater than the energy efficiency of CPUs. And that number 64 comes out of the ratio between the energy efficiencies of CPUs and GPUs. But also you notice that, yes, the charge is higher for the GPUs, but given the typical speedups of applications, we find that our accounting model rewards people using GPUs most of the time because the speedup they get using GPUs usually is worth that extra charge, but because then it's compensated by the shorter execution time. But if we were to charge, let's say if we were to choose a weight based on peak performances, then that multiplier will be much higher and would actually discourage people from using GPUs because they're too expensive, maybe for the workloads. So we would penalize people who cannot run very efficient GPU codes, but they could still benefit by using GPUs a little. That's a bit of a background, but we do also have a paper around this. A compute allocation essentially is an amount of service unit, as I said, that was awarded to a project that was successful in a merit application course. So people do not pay for to apply to use the supercomputer usually. They go through a merit application process, which means they award the time on the supercomputer based on the merits of their science. So it's an important science project. The government wants to support it, so we give them some time on the supercomputer. Each project that was awarded a service unit amount or an allocation as this allocation partitioned across the 4 quarters of the entirety of the project means that that prevents people thinking, oh, I will consume all the service unit the last quarter of the year. We want actually the supercomputer to be used throughout the years because we want to keep it utilized, and also we want to avoid the cases where people are not able to consume their allocation if they leave it to the last quarter. We provide we provide a tool that is called Pawsey account balance that monitors the amount of service unit you have available at any given time. So let's see if I have some. So this is an example of output. So you can see this Pawsey account balance tool, when run, shows the information about your default project. In this case, we are seeing that for the current information displayed is for the current quarter. We see that there are 250,000 service units available for this quarter for this project, and we've used 60% of it. This high is basically the part of the allocation that has been used when you request high priority. If you have important work, as will be explained later, you can request higher priority for your job to be run. This will be, I guess, accounted here. You can specify which project you want to, if you are part of several projects, you can specify which project you want the information to be displayed about, and so on. You can also break down by users. So you can see which user in your group is using most of the allocation. Any questions so far? Online? Is there anything online? Okay. So we learned what an accounting model is, what a service unit is, and what is a compute allocation. You have been introduced to the Pawsey account balance tool that you can use to monitor your allocation and make sure that you don't run out of the service units. On Cetonix, once you run out of your allocation, your jobs will lose priority. So we allow for you to use up to 150% of your allocation. At past the 100%, you will drop in low priority, but you will be still able to run jobs. After 150%, then you won't be able to run any more jobs. You should have been given a project and it has an associated allocation, and you can check the allocation of your project using this tool. Okay. There are no questions. This is the end for this part.